Okay, welcome to today's lecture. We're going to be covering Chapter 5, and this is part 2 of summarizing data numerically. What I have here is a couple of data sets, a couple of examples, and they're contrived to make a point. We have Class A with scores on, say, an exam or something like that of 73, 74, 75, 76, and 77. And Class B with scores of 55, 65, 75, 85, and 95. And let's think for a minute about how we might measure the center of these two data sets. And another way to think about measuring center is what was a typical score from Class A? So sometimes we call that the average score. And let's see. So for Class A, we could say the average score was the mean, or the sample mean, which is x bar. And if I added all those values up, divided by 5, I would get 75. We could also look at the average score for Class B. And notice if I added up all those scores and divided by 5, the average, mean score would also be 75. Also notice that the median, the middle one, in both cases is 75. And so we might conclude that the typical score from both classes is a 75. The problem here is, obviously, if I look at these two classes, they're not the same. And I think it's pretty clear that Class B has more spread. The scores are more spread out. So what we want to do is figure out how to measure this. How to measure this spread. So this is our question. And I think it's helpful to look at the scores using a number line. And I think the term I would use here is to think of the scores spatially. So I'm going to draw a number line. And right in the middle of the number line, I'll put 75. And then I'll put, I'm going to put 85 here and 95 here. Then I'll go the other direction and put 65 here and say I'll put 55 here. Okay, so those are Class B scores. And now within this range, let's see here, so 70 would be right about there. 71, 72, 73. My scaling's not quite right here, but I want to be able to write these numbers in here nicely. So this is just a sketch of the situation. Okay, so maybe put 73 and 74 there. 75, 76, 77. So if I were to put some markers here, some dots, say, to graph Class A scores, then what we would see is that spatially, or on the number line, Class A scores are grouped together much more, and I'll use X's for Class B, than Class B's score. So the thing to notice here is that in some senses, really what we're talking about here is the idea that overall Class B scores are more scattered out, or their distance, okay, if we look at, say, 85 and 75, the distances between those scores and, say, 75 to 95, these distances on the number line are much more than the distances for Class A. And so that's really one way to think about the differences between the two classes. Same measure of center, and again, if we thought about one way to think about the average or the mean is that it's the center of mass, and we could almost think about this as 75 as being the fulcrum. And both of those data sets would balance on the same fulcrum point or the same balance point at 75. But clearly the scores for Class B are more spread out. So we need, again, what we need is a measure or a way of measuring spread. Now, 75 is the sample mean for both data sets. So one way to think about the measures of spread are as follows. I'm running out of room here. Let's see. Let me see if I can do this well. So for example, if I look at Class A, okay, the difference between the data values, say like 77 and the mean of 75, which is 2, and say 76 and the mean of 75, which is 1. And then if I look at also the other side, which would be 73 minus 75 and 74 minus 75, these values would be -2 and -1 respectively. And notice 75 minus 75 would be 0. Now, these quantities we could think of as deviations. Okay, and again, I could do the same kind of thing for Class B. And if I did the same thing for Class B, notice that I'd have 95 minus 75, which is 20. That's a minus sign. And I would have 85 minus 75, 75, which is 10. And I'd have also, we'd have 55 minus 75, which is -20. And we'd have 65 minus 75, which is -10. So again, if we compare the two classes, it's clear to see that really what's different here about these classes are the deviations. And in some senses, this kind of tells the story. So we could actually perhaps even make an argument and say, well, here's the difference, and write this all up and say, here are all the deviations. But, you know, this data set's really kind of contrived here, like I said, because I only have 5 scores in each of these data sets. And sometimes in statistics, we're dealing with large data sets with 100 data values or 1,000. Or I even one time was analyzing a data set for a class where I had 5,000 data points. So in those situations, you know, we really need a summary number for this concept of measuring spread. Now, the first idea to work on here to think about is something known as the variance. And notice I've copied a formula right out of the book here. And I want to talk about this formula a little bit. Now, notice in the numerator of the formula, we have, within those parentheses, this is like the, for example, this is like the 73 minus 75. This would be, for the previous data set, what's in the numerator, in the parentheses in the numerator, is an expression that looks a lot like the deviations. And as a matter of fact, what is in the parentheses here are all of the deviations. Now, when we talk about the notation in front here, notice there's that sigma again. Okay, right there, and that recall that means sum. Okay, so what's going on in the numerator of this fraction are three things really, or maybe even more than three things depending on how you look at it. The first thing that's happening inside the parentheses are all these deviations are being subtracted, okay, and calculated. And then there's a square. So each of those deviations is also being squared. Now there's a reason why we have to square the deviations. And the answer is because if we didn't square these deviations, then the sum would always be 0. And if you think back to the previous example, if I go back there, I think I'll lose what I have, but I think that's all right. So it wasn't there. Never mind. Yeah, the PowerPoint erases everything when I move the slide. So, oh well. Now, all right, so let's talk about this just for a second more. So in the numerator of the expression here, we've got the deviations, and they're being squared. Okay, so these are the deviations, and they're being squared, and that makes them all positive. And then the deviations are being squared, okay? And then the symbol in front is a sigma, uppercase, S for sum. So what's in the numerator are the sum of the square deviations, okay? Now in the denominator, there's an n minus 1, okay? So this looks a bit like an average, like the mean average, because the mean average is the sum of all the x's over n, okay? And so in the numerator here, I have the sum of not x's like the mean, so the numerator is not equal to the sample mean. In fact, the sample mean is part of the calculation in the numerator. But it's sort of it is an average, and as a matter of fact, it's like a modified average, sort of like the sample mean. And also there's an n minus 1 here, and the n minus 1 sometimes is confusing to students because the n minus 1 is related to something we call degrees of freedom. Okay, so let me just take a minute. And the book talks about this. The textbook and the reading has a whole like a paragraph on this idea about how n minus 1 relates to degrees of freedom, which is an idea that is coming up in Chapter 10 when we talk about students' tea distribution. And also, if you're reading the Lady Tasting Tea, you may have already, Salzburg talks about this idea also in the Lady Tasting Tea. So you might have heard, if you're reading the Lady Tasting Tea, this term, degrees of freedom, might be familiar, or you might have heard it before somewhere else. The thing that I like, the way I think about degrees of freedom here in this example is, notice that, or in this application, notice that there's an x squared, or I'm not x squared, the sample mean, is part of the calculation for s squared. And by the way, I should also mention that notationally, s squared is the notation we use for something called the sample variance, okay? And we'll be talking about the variance and the sample variance specifically in more detail in the future. Okay, so what we have here in this formula is the sum of the square deviations divided by n minus 1 instead of n, okay? The variation, or the variance, is one measure of variation within a data set, okay? And what we have to keep in mind here is that this is like an average distance, but all those distances are being squared. So they're larger then their magnitudes are larger than the magnitude of the original data. So we're going to have to do something about that eventually. But right now, we're just talking about this basic idea. Sum of squared deviations divided by n minus 1, something called the variance. And the n minus 1 relates to this idea of degrees of freedom. There's two ways I like to think about the degree of freedom concept. First way, we're basing an estimate, or in fact, S squared is a statistic. So we're basing a statistic, which is an estimate of a parameter, on another estimate, the sample mean. So we lose a degree of freedom because of that. Another way to think about it, and another way to explain it, is by using n minus 1 instead of n, like we would for the sample mean, what we're doing is we're making the variance ever so slightly bigger, if you think about it, because instead of dividing by n, we're dividing by something that's 1 smaller than n. So the numerator is the denominator is a little bit smaller, so the overall measure of variation is going to be a little bit bigger. Another thing that's interesting is that the effect of subtracting 1 is going to get more and more pronounced as for smaller n. Let me be clear about this. So when n is a small number, like say 5, then n minus 1 is 4. Okay, so instead of dividing by 5, we'd be dividing by 4. That's a pretty significant difference. On the other hand, if we were dividing by 5, if our sample size was 5,000, then instead of dividing by 5,000, we'd be dividing by 499. So that wouldn't be as big of a deal. We probably wouldn't even notice the difference for this case. That's another element of this concept of degrees of freedom. It tends to be a more extreme adjustment for small sample sizes, because when we have a small sample size, we have more error. We would expect more error in all of our estimates. Anyhow, that's getting pretty theoretical, and I don't want to go too far with the theory. Okay, basic idea: the variance is square basically think of it as the average of the square deviations, sum of the square deviations. Now, I'm going to come back to another mathematical element, because I just can't resist. And this is, and you're not going to need to really be able to do what I'm about to show you, but I'm going to take a minute or two and do some math, do some algebra, because it's kind of a fun problem, I think. Of course, I see mathematics as recreational, and I know not everybody does, but nonetheless, indulge me. And I want to talk about the rest of this formula here, of this equation. Now, this last part here, this last expression on the end is useful. This is useful for hand calculations. So one of the reasons this particular formula is even in the book is because if we weren't using any kind of technology, if we weren't using the graphing calculator, the TI calculator for our calculations, then the formula, or the expression on the far right, and the fact that it's equal to the s squared on the far left, would be useful, because it'd make our calculations a little bit easier. I'm interested in showing you how, just giving you at least one example in this class about how algebra relates to statistics and how mathematicians use algebra. So notice in the middle here, we have an expression that looks really kind of complex. And that whole thing is equal to a much more simple looking expression on the far right. And what I want to do is take a minute and go through the algebra steps to show you how the numerator, which is x1 minus x bar squared plus x2 minus x bar squared plus dot 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 plus x sub n minus x bar squared. I want to show you how that's equal to n times the sum of x squared. And now I'm not going to use the subscript of I. I'm going to use a shorthand notation. When you put no subscript on the x, it means add them all up. So it's sort of like a math slang version of the full-blown notation. But I'm going to get tired of writing i's, so I'm just not going to write them. Now notice the n minus 1 is in the denominator on both sides, so I'm just going to leave that off because the algebra steps to show that that equation is equivalent is to show the simplified equation that I put down below here is equal. So I'm going to start with the left-hand side. I'm going to start with this left-hand side. And that sum, so what we have are the deviations squared, and all of them are being summed here in this expression. So what I want to show you is that this left-hand side, first of all, each one of those is a binomial square. So they're all quadratics, each one of those terms. And so, in fact, I can use the binomial formula to expand this. So the first term here in the first term in the sum above, it would expand to x sub 1 squared minus 2x sub 1 times x bar. And for the purposes of the algebra I'm going to do here, I'm going to write the times x bar, and I'm going to use x bar's formula, which is the sum of the x's over n. And then, of course, there's going to be a plus the quantity x bar squared. And again, I'm going to just replace x bar with sum of x over n. That's an n. And I'm going to square that. Plus, now the next term would have an x sub 2 square minus 2x sub 2 times x bar, which again, I'm going to write the sum of the x, all the x's over n. And then there would be a plus sum of x's over n quantity squared. And then there'd be plus dot dot dot. So this pattern would continue to the nth term, whatever that, however, whatever size n is. So like if n were 20, then this would go out until we got to x sub 20. But the 3 dots mean just continue the pattern. So the next thing that I want to do is think about what each of these things is equal to. Well, notice here I've got in the very first term in each one of these sets, I've got x1 squared, I've got plus, okay, x1 squared plus x2 squared, and then down here the next one would be plus, this would be x3 squared, etc. Okay, so what that actually equals is the sum of the x squareds. Now, think about these pieces, this piece and this piece, and think about what is common here. Is there anything I can factor out? Well, there's a negative. Okay, I'm going to factor out a negative here out of those two terms, those sets of two terms as we go down. So now I'm looking at this set of two terms, multiplication plus multiplication, multiplication plus multiplication. So I'm grouping all of those together, and I'm going to subtract off, I'm going to factor out a negative, and I'm going to factor out a sum of x's over n's. That's an x bar, but I'm just going to factor out a sum of x's over n out of all that stuff. And what's left behind? Well, all right, let me put parentheses here. Now I factored a negative out, but there's still a 2x1, okay, in there. Since this was a plus here, this was a plus here, and I factored out a negative, now I get a negative sign here, a subtraction sign here. And I factored out one of the sum of x's over n's, so there's one left. So I still have a sum of x's over n here. And then I would have plus, I got to look at these terms. Now this sum of x's over n and this sum of x's over n got factored out to here. Okay, so that's there. And let's see, so the negative here also got factored out. It's there. And so I have a 2x sub 2. Okay. And then that's going to be minus, because again, that was plus here, now it's minus. So that was minus, and then there's a sum of x over n. And in fact, I could think about what else is left in here. Well, there would be a plus 2x sub 3 minus sum of all the x's over n plus dot, 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 okay? And then I'll close the parentheses. So that pattern is going to go on until we get to the nth term, whatever that might be. So now let's have a look at what's going on in the parentheses here. Okay, so what do we have here? All right, so we've got the sum of x squared minus the sum of x over n times, okay, so this 2 here, this 2 here, this 2 here, there would be a 2 here, and on out to however many nth term, however many there are, could get factored out. And then notice the x1 plus x2 plus x3 plus x4 plus x5 all the way to xn, that is representing, or can be represented as a sum of all the x's over n. And then we would have minus sum of the x's over n, sum of the x's over n, how many of those terms are there? Oh, there are n of those terms. So we would have minus n sum of the x's over n, close parentheses. And in fact, I don't know why I wrote this in here, but that's a mistake. So that should not be there. That's going to mess up my algebra. I haven't tried my pen options. Can I erase? Pen color. I don't know. Oh well, I'll just leave it messy. Actually, let me rewrite that. I'll rewrite this line. So we would have the sum of the x squareds minus the sum of the x's over n times 2 sum of x's minus n sum of the x's over n, close parentheses. Now the n's here cancel. So let's see, you have the sum of the x squareds minus sum of the x's over n times, now I got 2 sum of the x's minus, those n's are gone, so that's minus, so there was 2 sum of all the x's minus 1 sum of all the x's. That leaves, 2 minus 1 is 1, so we have 1 sum of all the x's over n. Okay, so I'm going to run out of space here, so normally I would continue. Notice how this is how we do good algebra notation. I got all my equal signs lined up here on the left, and normally I would continue on down the page like that. Actually, I'm going to go to a new screen. All right, I actually have a clean screen ready to go. So we'll go here and I'll rewrite the line that we left off on. So where we left off on, with that algebra, I believe was here. We had sum of the x's minus sum of the x's over n. Oops, sum of the x's squared. Sum of the x's over n times sum of the x's. Okay. Now, this is equal to sum of the x squareds minus sum of the x's quantity squared over n. And now if I get a common denominator, which is n, have n sum of the x squareds over n minus sum of the x's quantity squared over n. And lo and behold, I've just derived the right-hand side from the previous screen. And so I have shown that the formula holds. So QED. All right, anyhow, just a little math fun. You don't need to know this. And in fact, the formula for calculating s squared, where s squared is equal to n times the sum of the x squareds minus the sum of the x's squared divided by n times n minus 1. Now I'm throwing that n minus 1 back in there because remember I just didn't bother with it because it was in both denominators on the left and right hand side. So it was just extra baggage. But in any case, this is for hand calculations. And we're going to use the TI for all of our calculations. So you don't really need to know this, but I thought I would just give you a little bit of algebra entertainment and show you that indeed there is mathematics, or many of the formulas in statistics involve some crazy mathematics. So okay, let's move on. So here's the formula again. Okay, I think what's important to remember is this version of the formula, because what this shows is the way to really think about the variance, the sample variance, which is as the sum of the square deviations divided by n minus 1. Now the next box down here is showing how we take the variance and calculate the standard deviation. So S is the sample standard deviation. Which is a statistic and therefore a variable. And of course, so is S squared. But notice, formulaically, S is the square root of S squared. So if you calculate the variance, take the square root of the variance, that gives you the sample standard deviation. And the difference between the reason we need S, or one of the reasons we need S, is because S squared is based on all the deviations being squared. So its magnitude is larger than the original data. So it's not as easy to compare S squared, the variance, to the original data as it is to take the square root, which brings it back down, that measure of variability, it brings it back down to the same magnitude as the data. And in fact, we think of the standard deviation as roughly an average distance of the observations from their mean. And if all of the observations are the same, then the standard deviation is 0, which means there's no variation, there's no spread. Otherwise, the standard deviation is always positive. And the more spread out the observations about their mean, the larger the value of the standard deviation. So if we go back and we think about the two classes, okay, the class data, and I'm just going to keep things simple here. I'm going to go stat and go edit, and I'm going to use list A1 and A2. Now I got A real in the middle, so notice I move my cursor all the way up to the top. I'm going to press delete. It's gone now. One point to make about what just happened, though, is that when I delete a list out of the editor, it's still in the memory of the calculator. So, and I'm just to show you, if I go to stat, or I'm sorry, if I press second stat, notice that list A real is still in the memory of the calculator. So now I'm going to go back to the editor, stat, edit. So deleting a list out of from the edit menu just deletes it out of the editor. It's like a shortcut almost, really. Okay, so Now I'm going to clear out, so I just highlighted L1, very top, cursor all the way to the top, press clear, and then down arrow or enter. That data's gone. Do the same thing here, press clear, down arrow. And again, I'm just making some space here. So 73, I'm putting in that grade data from that class A. So 73, 74, 75, 76, and 77 for class A. Class B was 55, 65, 75, 85, and 95. And so what I'm going to do is calculate the mean and standard deviation for the two classes. So I've just entered the data in the editor. I press second now, press mode, second mode, which corresponds to quit. Takes me back to the home screen. I'm going to go stat, calculate, one var stats. I'll do list one first. And what I see is the mean is 75 and the standard deviation here is about 1.58. Okay. Now let's do the same thing for class 2. So we're going to do calculate one var stats for list 2, press enter. Mean is also 75, same measure of center, but notice the standard deviation is about 15.8, which is much larger than the standard deviation from class A. So what we see here is the measure of spread, the average distance of the grades for class A from their mean is smaller than the average distance by quite a lot. And that's how we measure the difference between the two, the average distance. Here's another example. This is an example from the part 1 lecture. And here we're looking at salmon weights. And remember, we entered that into a name list, king salmon. So on my calculator, this is going to be in list K king S. Okay, and then I'll put a little L in front of there to indicate that it's a list. Okay, so that's the list that the data's in on my calculator. I'm trying to remember the mean from last class. Let's see if I remember it. X bar is approximately 30.5, maybe. I don't know. We'll find out. Okay, so let's go back to the calculator again. And this time what I'm going to do is one var stats again. So I'm going to go, now here's a shortcut. I could go stat, calculate one var stats like I did before. The shortcut is just to go second, enter. That brings up the last command. So I'll move my cursor back and I'm going to replace L2 with list king S, second stat for the list menu. I'm going to go down and find the right list, paste it in. Now, you could type this in off the keyboard, but the problem is you see the little L in very front of that list. That's necessary. And if you don't have that L, the calculator is going to give you an error. The easiest thing to do and the most reliable, or the most the process that leads to the least errors is to just go in anytime you need a list somewhere, just go second stat and paste it out of the list. And if the L needs to be there, the calculator knows and I'll put it there. Okay, so press enter. Oh, okay, well I guess I got that right. The mean was about 30.5. And notice what I'm really looking for is a measure of spread here. And the measure of spread is about 8.7. And so in this example, let's see, S is about 8.7, okay? And X bar is about 30.5. And notice the two numbers together, this is our numeric summary of statistics. Now, the other thing I want to talk about is the histogram from last class. Now, I've done a screen capture off the calculator and pasted the histogram in here. And notice there's a problem with the graph, of course. There's no scale here. And in fact, I just remember, what I actually wanted to do is show you how to draw this histogram on your calculator first. So let me go back to the calculator and let's talk about that histogram a little bit. And let me show you how to actually draw that histogram on your calculator, and then we'll go back and talk about the other stuff. Now, 3 steps to drawing a stat plot, okay? First step, put the data in the calculator. We've already done that. Second step, configure the stat plot menu. So I'm going to press second, y equals, takes me to the stat plot menu, and I'm going to select plot 1. Plot 1 needs to be turned on. You turn it on by using the arrow key. This is like a toggle switch. If I put my cursor on off and press enter, off is highlighted. Now the plot is turned off, but I need it on, so I'm going to move my cursor back there, make sure it's on. Select the right icon. This is the histogram icon. Press enter. Okay. Now, of course, I have the right list pasted in here because I did the this is left over from that screen capture. So I'm just going to clear it out like it wasn't there. So if you don't have any lists there, then this is what your cursor probably looks like. Now, interestingly, the calculator, usually when the calculator expects a list and the cursor is alpha locked at that entry, it's telling you that you should just type that list in because it doesn't need that little L in front of the list for the notation to tell the calculator that you have a list rather than a variable or the product of variables. But I'm not going to get into that detail right now. Okay, so I could type, there's 2 ways I could enter the list. I could type in KINGS, and I think that maybe that's even more keystrokes than pasting it in. So my habit is just to do the same thing, which is second stat, and then I remember that, well, no, I don't actually. I'll have to use I thought I remember which number was in front of the right King S, but I would have said 8 and I would have been wrong. Let's see. So I'll go down and find it. There it is. Press enter, paste it in. It may have been less energy to type KINGS here. I don't know. But in any case, 2 different ways to enter the list. Now, the plot window is configured correctly. The third step for drawing a stat plot is to configure the window settings. So I'm going to press window. And through some trial and error, I've discovered that this particular window setting makes a nice histogram. So what I'm doing is I'm starting the graph at 5. I'm going up to 50. That spans the entire data set. X scale equaling 5, that means the class width is going to be 5. So each bar in the histogram is going to be 5 units wide. And then the y's start at 0, go to 10. And then y scale is just telling us, or telling the calculator where to space out those tick marks on the y-axis. And then X resolution, you don't really need to worry about this. We'll just leave it at 1. Okay, and then once we have all that set up, we just press graph, and there's the histogram. Now, when I go back to PowerPoint, which is the histogram I've cut and pasted into this PowerPoint presentation, there's really kind of a problem here. And the problem is that there's no scale on the axis for one, and actually there's also no label. So there's like several things I don't like about the graph, but it is the type of graph the calculator creates. So if I were reproducing this on my homework, I'd want to extend that axis and label it with X. And I might even be inclined in this example to extend the axis to 0 on this side because it's only 5 units away. Remember, this left-hand boundary of the first bar is at 5 because on the calculator, that's where I had X min set. So this would be 10, this would be 15, 20, 25, 30, 35, 40, 45, and 50. And then I would just extend the y-axis on up. Let's see if I can do this. Halfway decent. Okay. And then label with y. These are the frequencies. So this would be 10. This would be 5. So on your homework, those details that I just drew in need to be there to get full credit on your graphs. You need to have axes, they need to be labeled and scaled. Now, one of the reasons why I wanted to show you this histogram is because I wanted to point out that if I think again of a fulcrum point, if I think of the sample mean as being the fulcrum point, remember the sample mean here was about 30.5. So if you look at the distribution, it looks like to me it would balance right there at the mean. And then the other thing to notice is that so I'll make a little notation here just to remind everybody. X bar was approximately 30.5 and S was approximately 8.7, or just about 9. And so if you think about the concept of average distance here, then if I go about just a little less than 9, I get to this point. So the distance from the sample mean to just right about there, that's 1 SD, 1 standard deviation. And I could also think about doing the same thing in this direction. And so that would be about 1, so that distance from there to there is about 1 standard deviation. And this distance would be about 1 standard deviation also in that direction. So if you think about that concept of measure of center, measure of spread, this mean and the standard deviation paired together give us the two pieces that we need to describe the distribution or the data set numerically. But there are other things we can talk about here. And in the future, what we're going to do, okay, down the road, what we're going to do is we're going to be talking about the idea of a normal distribution, okay? And this comes up first, I think, in chapter 6. And actually, it's mentioned in other places, but not in detail. So I'm just going to kind of draw a little mini graph here. So the salmon weight data, I think I mentioned, or I know I mentioned when we first started talking about it, I sampled that from a known normal distribution with a known mean, okay? And the actual mean from the population. So this little micrograph I'm drawing here is a population, okay? So this is how I'm envisioning the population. Now again, this is theoretical. This is hypothetical even, because this is representing all the salmon in the ocean on the earth. There's no possible way I can prove that the population follows a bell curve. I've got to assume it. But the cool thing about this particular data set is I sampled it using the calculator, and I told the calculator what the mean and the standard deviation was. And the mean and the standard deviation that I used to generate the data set was a mean of 30 and a standard deviation of 10. So this data came from this particular distribution. Now, when we get to chapter 6, okay, you're gonna learn about something known as the empirical rule for normally distributed populations. But I like to, like I said, I like to foreshadow those things and do some stuff in parallel, like in this case. Now, okay, so the empirical rule would tell us that, okay, so let me do one more thing, okay, before I forget. So I'm going to introduce a notation that comes up later. N for normal distribution, 30 for the mean of that distribution, and then comma 10 for the standard deviation. So this is the notation we use for a normal distribution that has a mean of 30 and a standard deviation of 10. Now I know I'm using some symbols and ideas here you're unfamiliar with, but we're going to be using these down the road. So don't worry about that too much. Now, the empirical rule says that about 67% of the population lives within 1 standard deviation of the population's mean. So when I come into this data set, I could ask that same question. Does about 67% of the values fall within 1 standard deviation of the sample mean? Well, I'm not going to bother to do the actual counting and make the calculation, but it looks like it's pretty close. Maybe a little bit more here in the middle than we would expect, but it's in the ballpark. And then the other thing about, there are other pieces of this idea of the empirical rule. And the other thing the empirical rule says is that if we go another standard deviation, then we've captured about 95% of the population, okay, when we go 2 standard deviations. And this is only for normally distributed populations. And so we could think about this same example and think, okay, if I go another standard deviation here and another standard deviation here, and again, I'm just ballparking it, have I captured about 95% of the sample? And it looks like I have. So basically, and there's a couple of different problems in the book that are talking about this as well. But this is another way to think about it, okay? Okay, now let's talk a little bit about parameters, okay? And I in the previous example, I was using mu for the population mean, and I was using sigma, lowercase Greek letter sigma, for the population standard deviation. So, if you actually have all the population observations, and notice we're using capital N here for population size, then the population variance is the average of the squared deviations of the observations. So what does that mean? Well, why are they saying is the average? The reason is because there's an N here instead of, okay, instead of the N minus 1. So that makes what's under the radical here an actual average. Now, we're allowed to use N instead of N minus 1 because we're not estimating here. We have mu, okay? This is known in this case. So there's no need to make an adjustment. We have the exact population mean. We have all the x's. We have all the x's from the population. So we now know the true, quote, standard deviation. And so this is important when we look at the calculator output as well, because when I go back and I look at the calculator output, okay, I'll just go back to any of these examples. I'm just going to go second enter. So we'll look at the salmon data. Notice there are two different standard deviations. There's S sub x, and incidentally, the calculator uses a slightly different notation than the book. The book uses S, and most statisticians use S as well for sample standard deviation. But the calculator uses S subscript x, means the same thing. This is the sample standard deviation, S sub x. Sigma sub x is the population standard deviation. So notice the sample standard deviation is a little bit bigger. The problem is, and this is hard to explain, I'll do my best. The problem is the calculator, how will the calculator know whether the list that we're taking one var stats on represents an entire population, a small population, yet the entire population, or just a data set or a sample from some population? And the answer is the calculator really doesn't have any way of distinguishing. So instead, what happens is we get both possibilities, and we have to know which one is correct. So we use the S, the sample standard deviation, if there's a sample in the list that we're analyzing, and we use sigma if that list represents the entire population. Now, in most practical applications, we're not going to have the whole population. I mean, that's a very rare thing. Most of the time, the correct number to use in your calculations and in your analysis is S. So if you have to guess S. Let's see. So the other thing to talk about here, the other thing I want to talk about here, okay, yeah. All right, so I want to be clear about this. We've got sample statistics, okay? And that is, those are x bar. X bar is the sum of the x's over n. And we have population parameters. And again, we don't usually, saying the word population parameters is really redundant, but now these two formulas are going to look pretty much the same, and that's why the calculator doesn't need to print out a separate mu either in one bar stats, because really the formula is the same either way. And then the sample standard deviation is the square root of the sum of all of the square deviations divided by sample size minus 1. And sigma is equal to the square root of the sum of all the x's in the population minus the population mean, all those deviations squared, divided by capital N for population size. So this, now the other point I want to make, and this is going to be important in the future as well, x bar estimates mu, S estimates sigma. Okay. In every instance, the statistic estimates the corresponding parameter. Every statistic has a corresponding parameter and vice versa. Every statistic estimates that parameter that it corresponds to. All right, let's move on to a different idea here. Percentiles. And again, this is probably a term that you've heard of before and maybe even understand completely. But let me read the definition. The pth percentile is a value such that p% of the observations fall at or below that value, and 100 minus p% of the observations fall at or above that value. Okay, so what does that mean? Here's another data set, and I just made this up. These are some exam scores, okay? So I mentioned in a previous lecture in part 1 that the median is the 50th percentile. So using this definition, what would be the 50th percentile? Well, it would be the number, or it would be a number such that 50% were below that number and 50% were above that number. And so we could think that probably that number's got to be somewhere in here. Well, there are 20 exam scores here. So if I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's see, there should be 10 on the right. Let's just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. So the dashed line that I just wrote, or I just drew in here, is at, this is in some sense at the 50th percentile. The problem is there's no number here. Okay, and that's going to always happen when there are an even number of data values. Okay, if they're like 10, there would be 5 on one side, 5 on the other. 20, there's 10 on one side, 10 on the other. Anytime that we have an even sample size, then there's going to be no number here. But that's okay, because what we do when there's no number here is we call the median the average of the middle two. So to calculate the median, I'm going to look at the middle two numbers and then just average them. So I'll take 77, and this average in the sense of the mean. So 77 plus 78 divided by 2 is 77.5. So the median here, or the 50th percentile, is 77.5. And notice that percentile doesn't necessarily have to be a data value within the data set. And then the other idea in the book, the textbook talks about, is this idea of quartiles. Okay, so the quartiles are at the 25th and the 27th percentile. Okay, and unlike the median, the first, what we call the first quartile, is a value somewhere on the left where 25% now. Okay, so let's talk about the quartiles. Okay, I'm just going to Get rid of that stuff. Let's see. I'll put the dashed line back in here for the median, and let's talk now about the quartiles. Okay, so first quartile, 25%. Well, let's see. 25% of 20 is 5, so there should be 1, 2, 3, 4, 5 scores below, and there should be 15 scores above. We call this, the notation we use here is Q1 for first quartile. And again, there's no number here there's no middle number, so I have to average the middle two numbers. Let's see, that's over 2. So what's that going to be? 67.5, I believe, for Q1. And then we could do the same thing down here for the 75th percentile, which means 75% below. 75 percentile means P% fall at or below, 75% below, and then 25% above. And again, there's no middle number, so I'm going to average those two. So Q, and then we use Q3 as the notation for the third quartile. And let's see, 83 plus 85 divided by 2 is, I believe, 84.5. So the quartiles here are 67.5, 77.5, and 84.5. So why did I put 3 numbers for the quartiles? Well, these 3 numbers are actually the 3 quartiles. This is Q1, this is Q2, this is Q3. We also happen to call Q2 the median, but notice they're quartiles because they divide. These 3 numbers divide the data into chunks that are each 25% or quarters of the original data set. So that's where that word and idea quartile comes from. Now you can almost see a summary, kind of another type of a summary happening here numerically. Okay. And if we go back to our 2 number summary idea, okay. So if we and I said earlier, I think I said you need 2 numbers, a measure of center. So if we measured the center using the median, 77.5, then we'd want to, and again, remember the median is based on percentiles. Then we also want probably a measure of spread that's based on percentiles as well. And actually, the measure of spread that corresponds to the median is called the IQR, and that stands for interquartile range. And the IQR is equal to Q3, 84.5 in this case, minus Q1, 67.5. And simplifying here, what do we get? So it's going to be a 0.07, and I borrowed 1. I think that's a 17.017 is the IQR. Just for fun though, I think I want to, should I check that on my calculator or do I trust my subtraction? I'll do it by hand this way. I'm almost positive I'm right, but you know, everybody makes mistakes. So let me just do it here. Let's see, that's 0. I'm going to borrow 1 from 7. So there's my 7 and then 17. Okay, so there we go. So the interquartile range here is a single number, 17. Notice measure of center, 77.5, measure of spread, 17.0. And we can also think about, or we should also think about the interquartile range as a distance, okay? Because notice that here is, now, and again, importantly, the interquartile range is not any kind of subtraction or adding from the median or anything like that. So it's different than the standard deviation in that sense, and that's important because remember, we use the median as a measure of center when we're dealing with symmetric distributions, and we use, I'm sorry, I said that wrong. We use the mean when we're dealing with symmetric distributions, and we use the median when we're dealing with skewed distributions. So that idea of these statistics being based on the positions of the numbers or their percentiles rather than distances, strictly speaking, is good. But in any case, the IQR spans the middle 50% of the data. So 25% and 25% is 50%. And so notice the IQR is spanning that middle 50%. So we have a measure of center, the median, measure of spread, the IQR. This is the second way that we can describe data sets numerically. Now, just to kind of give another example of this percentile concept, I wanted to just demonstrate the 90th percentile. So what would the 90th percentile here be? Well, to calculate the 90th percentile, what we would do is we would figure out how many data values I've got to go to cover 90% of the data. And so if I've got, the n is 20, okay, then 90% of 20 is 18, which means I should count 18 data values, and 88 would be what I would call the 90th percentile. And remember, the p% have to fall at or below. So that's how we calculate the 90th percentile. Okay, now I want to come back and talk about IQR and another idea called the 5-number summary. The 5-number summary for any data set consists of the minimum, the first quartile, the median, the third quartile, and the maximum. So if I go back here to this particular data set, okay, the 5-number summary, okay, would be 32, comma, that's the minimum. And then I would find Q1, 1, 2, 3, 4, 5. And that was, what was that, 67.5, right? I think. 67.5. And then the median was 77.5. The third quartile was 84.5. And then the maximum was 98. So that would be the 5-number summary for this previous example. Now notice there's also a graphical representation, and we call this a box plot. So notice the box part of the graph, I'm going to do, the calculator can draw these, so I'll do one of these on the calculator as well. But the calculator, so the box, notice, represents the IQR. The line in the box is the median, okay? And so, and then the whiskers go out to the minimum and the maximum. Okay, so let's look at an example here. I took this right out of the textbook. And so now we've got age data. And there are 20 subjects in the study. And our question is to like summarize this in some way. Now, when I look at this box and whisker plot, okay, this tail is going out here quite a ways, and it makes this distribution look somewhat skewed, okay? And I'm not sure it is, really, but it kind of looks that way. And the reason I'm not sure it is because when I look at the data, the smallest data value here is 32, but the next one's 37. So if I were to graph that, then there's a data value here, like right at 37. And then if I go one in here, then I'm at 50. So the question is, you know, when the tail goes way out here like this, is it really showing that we got a really skewed situation, or is there something else going on with this value? And specifically, what could be going on with this value? Well, the question I might ask is this value something we call an outlier? And what is an outlier? Well, an outlier is a data value that's very different than the other data values. And there isn't like necessarily a hard and fast kind of rule to define what an outlier is, but there are some calculations we can do. And in fact, the book uses something called uses a formula known as 1.5 times the IQR. So to figure out what an outlier is, what we do is we say anything that's more than 1.5 times the IQR above or below Q1 or Q3, we're going to call that an outlier. So let me show you graphically how this works. So the distance from here to here is the IQR. Of course, half an IQR would be the distance from here to here. That would be a half an IQR. So if I visualize taking that chunk and extending this by about a half an IQR, then the distance I'm really talking about is roughly this distance right here. And I'm going to eyeball it. But if I take and I go that 1.5 IQR distance, just eyeballing it, then there would be a cutoff point like right here. And then again, if I do the same thing on this side, roughly the same distance, notice there are no data values that are beyond that cutoff point. So using that, and again, I want to clarify the distance I'm talking about here from Q1 to this kind of like this boundary. This is the distance is 1.5 times the IQR. Okay, and it's a rule. It's just it's a convention, okay? Any data value that's more than 1.5 IQRs below Q1, that's the case with the 32, or above, or 1.5 IQRs above Q3 would be considered an outlier. So for example, 51 here is not an outlier because 51 is easily within 1.5 IQRs. 32 is an outlier because it's more than 1.5 IQRs from Q1. I think I just did everything I wanted with this graph in the previous screen. So let me go on here. All right, now look at this process, okay? I mostly flash this up here because I want to, and it comes right out of the textbook. I wanted to kind of make a point about how that some of the places in the textbook where there's a lot of busy work. This is like, to me, a lot of busy work. Now, if you don't have a calculator that's capable of identifying outliers, then yeah, you need to know this. But how many people are really going to remember all of this? I guess some will, but I'm not sure that this is all that important. But this is basically what I just described in the previous example, okay? We got to find the IQR, that's this step. We got to compute the quantity 1.5 times the IQR, that's this step. That's going to be a number, that's just going to be some number. And then we create these things called the inner fences and the outer fences, lower fence, upper fence. Well, those were the boundary lines that I drew in the previous example. Now, another one of the examples we talked about before, and you know what, I'm going to go back. I'm going to go back to this example. I want to show you how to do this on the calculator. This example is worked out in the textbook. If I remember correctly, the calculator steps are included as well. But just for completeness, I think I'm going to, wait a minute. Is this going to work? All right. Maybe I'm getting ahead of myself here. Let's see. All right. Okay, I'm to do it that way. Let's just for practice, let me show you how to enter this data and actually show you what I'm talking about with the calculator here. So I just press stat, and I pressed enter, which took me to the list editor. And let's use L3 for this example. And it actually, at this point, it doesn't matter what list you use, as long as you are on, if you use a different list than me, just make sure you're consistent on your calculator. So I'm going to go ahead and enter the data. And the fact that I only have 19 entries tells me I probably made a mistake. So I'm going to go back and check them here. Let's go back to the top, see 32, 37, 39, 40, 1, 2, 3 41s, 42, another 42, 43, 44, 45, 45. Oop, need one more 45. So I'm just going to go second, delete to insert, and then make that a 45. So let's see, I got 3 45s, 1, 2, 3, yep, and a 46, 2 47s, a 49, a 50, and a 51. Most common statistical mistake, data entry mistake. All right, anyway, data's in L3. Now, if I wanted to calculate the 5-number summary on the calculator, one way to do it is to go stat, calculate, 1-bar stats, second L3, because I put the data in L3. Excuse me. First, the first output is the sample means, sample standard deviation, n is 20, sample size is 20, but the 5-number summary is down below. So if I arrow down, notice the calculator is printing out the 5-number summary, the same values that that the textbook has in the example. Now, when I wanted, the main reason I wanted to go back and look at this data set on the calculator is because I wanted to show you how to draw the box and whisker plot that we're seeing in the example in the calculator. And again, the box plot is a stat plot, 3 steps. Step 1, enter the data. Step 2, configure stat plot. I just press second function y equal. Might as well use plot 1 again. Now, I'm using the right arrow. Notice I'm right arrowing to this box, and then I'm going one more, okay? This icon is the box plot, or the box and whisker plot. So I'll select it, and then I need to change my X list because I want to do the example in the book. So I'll clear out what's there. I'm going to go second 3 to paste in L3 because the data in my calculator is in list L3. And then the third step is to configure the window settings. So I'll press window. All right. I don't know why my calculator does that. Okay, so the smallest data value is 32. I'll just make x-min 30. That should work. The largest is 50, so I don't know. I'll make that 55 maybe. X scale works fine. Y, min, and max don't actually make too much difference here, as long as it's something the calculator can draw, because I just press graph, because the box plot doesn't have a vertical axis ever associated with it. It's only a horizontal graph. Only deals with one variable, the x variable. There's no frequency axis or anything like that here. So notice the graph on the calculator looks similar to the graph in the book. Now, if I want to show the outliers using the calculator, what I need to do is something called a modified box and whisker plot, which is another kind of stat plot. So I'm going to go back to the stat plot window, second y equals, and I'm actually going to configure plot 2 instead of plot 1. So I'm going to select it. I'm going to turn it on by pressing enter on. And this time the icon I'm going to pick is this icon, the box plot with the little dots. And what this graph is going to do is draw the box and whisker plot, and it's also going to identify outliers using the 1.5 times the IQR rule. Now, of course, the X list here, instead of L1, I need to put in L3. And then I'll press graph. Now, since I have plot 1 and plot 2 both turned on, this is the graph that we end up with. These are side-by-side box and whisker plots. And notice there's space for a third one, and we can configure 3 plots at once. So we could look at as many as 3 box plots side by side on the calculator, which is sometimes useful. But notice the thing here is that the data value corresponding to 32 is being identified by the calculator now as an outlier. Oh, incidentally, if I want to see the actual numerical values, and this is important on the calculator, I need to do a trace. So if I press trace now, the calculator shows me for the first plot, the median is 43.5, and if I arrow to the right, Q1 is 41, and if I arrow to the left, it tells me the minimum X is 32. Now if I scroll down to the second plot, notice that tail just goes to an X value, so the calculator says that value at the end of the tail there is 37, and if I go one more to the left, I get the minimum data value, which is 32. Now, when we do a modified box and whisker plot like the second one, the data points that show up like dots rather than having the whisker go all the way out to them, those are the outliers. Okay, and again, the calculator is using that 1.5 times IQR rule. 1.5 to IQR is below Q1, or 1.5 IQR is above Q3. Those are outliers. Box and whisker plot is a picture of the 5-number summary. Notice that 5-number summary is minimum, Q1, median, Q3, maximum. Let's see. Now let's take a look at the real estate data for a moment here. And recall that the histogram, wait, did we draw? Oh yeah, we did draw a histogram for this. The histogram for this was demonstrated or showed a skewed right distribution. All right, but before I get to that, let's take a look at, let's analyze this data set using the calculator. Now, last class, I entered this data set as Arcata real estate. All right, and let's see now. Let me go ahead and this way we can see both the calculator and the example. Okay, so last class we entered this data into the calculator, if I remember right, in the previous video, and I have it already in my calculator. So first thing I want to do is look at some of the summary statistics. So I'm going to go stat, calculate, 1-bar stats, the list. I'm going to go second stat to get to my list. That's Arcata real estate. That's number 7. Press enter. So what we see here is the sample mean is about $384,200 roughly, and the sample standard deviation is about 197,000 or about 200,000 or so. Now the other set of summary statistics that we can look at are the median and the interquartile range. So notice the median here is about 327. That's a lot less than the mean from before. And the interquartile range is still right around, what? Right around 200. It's about 210. So measure of center and measure of spread using the median and the interquartile range would be the other way we could summarize this data set. Now, one of the things I want to demonstrate with the box and whisker plot, I'm sorry, box and whisker plot. I mean, one of the things I want to demonstrate with this histogram, okay, and also I'm going to go ahead and throw the axes on here. Let me get my pointer here. It's pen, and let's see. All right. So let's see here. Right now I have no label on the axis, so I'm just going to put an X on there. And let's see. And then this would be corresponding to the y-axis, and this was 5 and 10. Remember that. I'm trying to remember where we started this. We started this at 150,000. And we counted by 50,000. So this would be 200,000. This would be 250,000, 300,000, 350, 400, 450, 500, 550, 600, 650, 700, 750, 800, 850, 900, and we ended on 950. All right, so there's my scale on both the x and the y-axis. Now let's go back and talk about the sample mean here for a second. The sample mean was about 384,000. So 384, this is 350. So 375 would be like right about here. So 384, that's going to be a point right about there. And again, if I think about this like as where the distribution's fulcrum point might be, notice that there's the sample mean. Notice that it's got to be moved to the right here a little bit, okay? And that's because these values over here. Now, I'm going to spend a minute just talking about physics. Now, if like these represented like weights being stacked on a uniform bar or something, then the idea here is that the further out these points get, the more leverage they're applying, the more rotational force they're applying around this thing we call the center of mass. And so even though the 50% of the data values, what was that? That was, I think that was like 325, or the median was somewhere in here, like at 325, or I can't remember, 324. But the median was back this way, right about there, if I remember right. So that means 50% of the data values are below the median, but since these are further out, the mean's got to be shifted to the right, okay? So that's the idea of why that mean gets skewed that way. It's involved in a sum of all of these values, so that's mathematically what's going on. Measure of spread corresponding to the mean, it was S, and S was about 200 here, which means that, you know, if we go 200,000 in this way and 200,000 in that way, if we had a normal distribution, we'd expect about 6-7%. But I don't even want to talk about these statistics right now because this is clearly a skewed distribution. So really the appropriate summary statistics to use are the median and the interquartile range. So that real estate data set described numerically and graphically would look like this, okay? And again, I'm going to go back to the calculator to look at this. So the 5-number summary, oh, I was off a little bit. It was 327, not 324, but that's okay. It's no big deal. So the 5-number summary is 175, 249, 327, and 459, and let's see, 925, okay? I'm going to need that. And then the other thing I want to do is I want to draw the box and whisker plot for this example. So now I'm going to go here back into stat plot. Again, the 3 steps for a stat plot: enter the data, configure the stat plot window. So I'm going to use plot 1 for this graph. I'll go here and I'm going to switch to modified box plot. The list I want to do is not list 3. I want to do, I'm going to go second stat to get to my lists, and then number 7 is the list I actually want to graph here. And then the next thing I need to do is set up my window. Now, let's see, the window, let's use the scale I used before. What was that? Excuse me. Well, I'll just start at 100,000 and go to 950,000, and I'll just count by 50s here. Let's see what that looks like. Now, again, one of the things that's kind of nice about the graph is that, or the calculator, is that I can look at these graphs. I can redraw this so easily that I can modify, it's not a lot of difficulty to adjust the window settings to get the graph to fit nicely. Now, let's see. This is kind of fun. This particular software I'm using on my calculator lets me take something called a screenshot and copy it. And let's see, I can go back to my PowerPoint here. I should have probably done this earlier, but okay, you're seeing me modify my PowerPoint slides on the fly. So this is the graphical representation, a modified box and whisker plot. Notice the calculator is showing these 3 data values on the far right as outliers, meaning they're unusually large, okay? And again, if we look at this spatially, you can see this distance right here and right here. That's the IQR on the graph, that distance. And notice if I go about a half an IQR or so, and I think about going from Q3, that's kind of making sense there, that distance. Just eyeballing it, those 3 values, outliers. And then the other way, the way to describe this numerically would be using the median, which is going to be equal to, what did we say that was? 327. And then the interquartile range, which is a single number, the IQR here, which is about, that was at 210. And that came from, that was the Q3, which was 459 minus Q1, which is 249. That's equal to 210. So that's the IQR. That's where the IQR came from. And then we can also, so this would be like the 2-number summary. Measure of centers, the median, measure of spreads, the IQR. And then we could also write the 5-number summary as well. And the 5-number summary would look like this. It'd be 175 for the minimum, 249 for the first quartile, 327 for the median, and 459 for the third quartile, and 925 would be the maximum. So the box plot using median and interquartile range would be the most appropriate way to summarize a skewed data set like this real estate data. All right, well, that's the end of this presentation. So I'll post this up on my webpage, and hopefully it'll all work out. And I think this new way of doing these presentations is better. So I'm going to probably continue this. All right, have a nice day.